Para comenzar el evento, le voy a pedir al doctor Arturo Olvera que nos hable un poco sobre David Alcaraz. Por favor, Arturo.
Buenas tardes a todos, muchas gracias por asistir a esta conferencia dedicada a la memoria de David Alcaraz y voy a tratar de hacer una muy corta semblanza sobre la vida académica y el desarrollo que tuvo David en esta institución. David ingresó en la Facultad de Ciencias muy al principio de la década de los 70 para estudiar la carrera de física. Él concluye esta licenciatura elaborando una tesis que está relacionada al área de físico-matemáticas, particularmente sobre la teoría de grupos y ecuaciones diferenciales. En su segundo año de la carrera ingresa a este instituto, al departamento de cómputo, donde empieza a hacer una labor de cómputo muy importante. En 1976 es aceptado en Berkeley para realizar su doctorado en matemáticas, pero por problemas presupuestarios de CONACYT tuvo que regresar a México porque hubo en aquella época una crisis de falta de presupuesto para los becarios. Mientras tanto, decide estudiar la maestría de matemáticas en el CINVESTAB y continúa al mismo tiempo su labor en el departamento de cómputo de este instituto. Para 1979 logra ingresar al doctorado en la Universidad de Cambridge y luego en Oxford, bajo el apoyo del Consejo Británico, y realiza su posgrado con mucho éxito durante este periodo. Su tesis doctoral la realiza bajo la supervisión del profesor Benjamin, que era uno de los grandes expertos en teoría de fluidos en la Universidad de Oxford. En su tesis estudió el problema de la creación de vórtices en flujos cortantes, donde desarrolla soluciones exactas para vórtices de tipo ojo de gato. Para lograr este estudio usó una combinación muy heterodoxa de herramientas matemáticas, tanto de análisis no lineal, teoría de grado, métodos variacionales y teoría de bifurcación. A finales de 1983 regresa a México y para principios de 1984 ingresa al Departamento de Matemáticas y Mecánicas de este instituto. Desde su incorporación empieza una colaboración muy fructífera con los distintos miembros de este departamento y como una de sus labores importantes, dado su conocimiento previo en computación, crea el primer laboratorio que tuvo nuestro departamento en aquella época. El 19 de septiembre de 1985 fallece debido a el terrible terremoto ocurrido en esta ciudad, cual pues, fue una gran lección para nosotros esto haya sucedido. Cuando debemos de hablar de una persona que estaba llena de virtudes, es muy difícil hablar de cuál es la que más nos llenó, la que fue más notable, pero yo creo que todos aquellos que llegamos a conocer a David, quizás la primera que nos viene a la memoria fue su gran generosidad, porque nos pudo a todos dar una serie de conocimientos, experiencias que todavía las conservamos en nuestra memoria y que pues, nos mantiene vivo su imagen todo el tiempo con él. Él tuvo una preparación académica muy importante, muy interesante, porque supo aplicar en las ecuaciones diferenciales métodos muy distintos, tanto en las áreas duras de la matemática como el análisis, la topología, la geometría y la sintótica, junto con las herramientas computacionales. Quizás fue la primera persona en la universidad que tuvo esas capacidades de conjuntar todas estas herramientas. Ya para concluir, déjenme decir que si bien el destino truncó la carrera académica de David, pero para nosotros sigue siendo una gran inspiración para el desarrollo de nuestra labor académica y creo que siempre lo vamos a tener muy presente a él. Muchas gracias.
Pues voy a proceder a presentar al profesor Richard Montgomery. Entonces, es un placer tener aquí con nosotros al profesor Richard Montgomery, que es profesor de la Universidad de California en Santa Cruz. Entonces, el profesor Richard Montgomery es un experto en aplicar métodos de geometría diferencial a problemas de mecánica, pero no solamente se limita al uso de la geometría diferencial, sino que son varias áreas de matemáticas las que utiliza en su investigación, entre ellas el cálculo de las variaciones, técnicas de sistemas dinámicos, teoría de grupos de Lie, topología e incluso un poco de geometría algebraica. Entonces, en los años 80 hizo una contribución importante al aplicar teorías de gauge, que generalmente se aplican a problemas de física teórica, a un problema muy clásico que corresponde a lo siguiente: cuando un gato va cayendo hacia el suelo, ¿cómo hace el gato para caer sobre sus cuatro patas, ¿no? Entonces es un problema muy fácil de plantear, muy sencillo, de mecánica clásica, al cual pues técnicas de geometría diferencial pueden ser importantes, ¿no? Este problema resulta que tiene relación con problemas de isoholonomía y control óptimo, y metiéndose en esta área se dedicó a la geometría subriemanniana, en la cual escribió un libro que es un clásico moderno en el área de geometría subriemanniana. Pero su contribución por la que es más reconocido es por sus contribuciones al problema de los tres cuerpos, que es de lo que nos va a hablar hoy. Entonces, en el año 2000, junto con Alain Chanzinet, redescubrió la solución de la figura 8 para el problema de los tres cuerpos, que dio lugar a pues toda una microindustria de coreografías, y bueno, pues fue, digamos, un trabajo seminal en el área de las coreografías y en el problema de los n-cuerpos, pero tiene otras contribuciones más generales a este problema. Adicionalmente, tiene contribuciones importantes en geometría diferencial, en la clasificación de las singularidades en lo que se llaman distribuciones, ¿de acuerdo? Distribuciones como en geometría diferencial, no como en deltas de Dirac y todo eso, y donde también entran técnicas de geometría algebraica. Bueno, pues es un gran placer tener aquí a Richard, y pues le voy a ceder la palabra, esperando que nos puedan ver en Georgia Tech y en el Politécnico.
Muchas gracias por la invitación. Es un gran honor, big honor. Okay, we begin with a tour of, just to get situated. Think about these are the famous ones that Kepler found, the Earth going around the sun. We think of it in a circle, but it's a ellipse, slight ellipse. And this is two equal masses moving, and a solution to these differential equations. We're going to have some equations. So Newton's equations, mass times acceleration is force. There's a force of 2 on 1 and 1 on 2. They're equal and opposite. They look like 1 over the distance squared. So there's the formula. So these are essentially the reason Newton wrote the Principia. His big victory was solving these equations and writing down differential equations. So that's for two bodies. That was in about 1660 something. And then about 100 years later, the first explicit solutions to the three-body problem, Lagrange 1772, Euler 1767, and they're the only solutions that we explicitly analytically know. You cannot write down closed form formulas for any other solutions. There's many, many solutions, but you cannot write them. No one knows how to write them down in a closed form way. I'm going to show you those solutions now. So in the Lagrange solution, the bodies stay in an equilateral triangle at every instant. And I'm not a pro with the computer. The equilateral triangle should spin with the bodies. It doesn't. But they're an equilateral configuration at each instant. So they can move around a circle, or ellipses, or hyperbolas, or straight lines, any conics. So I'm going to show you a few. Oh, what are the equations? Now we have extra forces. There's a force of the blue on the red. Let's see if we can. No. Well, you have the three bodies. So body 1 has a force from body 2 and body 3. The forces look the same as in the previous slide. So it's a coupled system of 1, 2, 3. I like the plane. So 6 second-order differential equations in the plane. So that's the planar three-body problem. And here's some more solutions of Lagrange. How they're moving in conics, in ellipses. The ellipse can be any eccentricity. They're all the same eccentricity. For all these motions, this ellipse is similar to that ellipse is similar to that ellipse, and that's the way it always works for the central configurations. And here is my personal favorite. Okay. This one down here is the Lagrange collision ejection solution. So they're at an equilateral. You start them off at rest in an equilateral triangle. They shrink and collide in a triple collision, and I artificially let them bounce out. Better way to think of it is they explode out as a triple collision and shrink back. And I call this the Lagrange collision ejection solution. It has angular momentum 0. The velocities go to infinity at triple collision. Can everybody hear me okay? Yeah. Okay. So these are the only ones we know. I forgot Euler. I don't have an animation of Euler. Euler was the first one discovered. They stay in a line at each instant. And the ratio from the blue to the white and the white to the red would stay the same. And white would always be in the middle. And the same trick works that Lagrange used. So you can have these moving in a circle. It's easy to imagine if all the masses are the same. What Euler observed is for any mass ratios, there's solutions like that. So when we classify them, there's 3, depending on what mass is in the middle. To explicitly solve for this, he had to solve a quintic, a 5th-degree polynomial, probably the first time. So these are the known solutions, explicitly known. And I jump forward now to Poincaré, who there was lots of work in between. We're just doing a brief tour. So in around 1892, he discovered what we call chaos nowadays. It's a wonderful story where he had to pay a lot of money to withdraw a journal because he had an incorrect result. It's a really interesting story. You cannot see chaos with a single orbit, but you can see something interesting. So I just grabbed this. If you're interested, there's a wonderful page in Scholarpedia called Three-Body. It's just a Three-Body Scholarpedia. Google it. And I just grabbed that from there. Rick Mokel made this picture. It's called a transit orbit. So think of this as the Earth and the Moon. This is a rotating frame. So viewed in an inertial frame, the Moon's going around the Earth. And here's a little satellite doing that dance there. This is now the 70s. The person who did this was Piotr Hut. He has a book with Hegel called The Million Body Problem. And they used here, 1 and 2 are coming in a Keplerian orbit, and 3 is coming in. And then there's a very complicated mess going on, and then 1 and 3 go out, and 2. So this is called an exchange orbit, and these were important in trying to understand globular clusters from a statistical mechanical point of view. They did lots of three-body motions. This is the thing that I got famous for with Chansonnière. The person who actually discovered it is a little bit bitter at times. His name is Chris Moore. He works at the Santa Fe Institute. He did his degree with Phil Holmes. Some of you might know Guggenheimer and Holmes' book. He wrote a beautiful 2-page paper called Braids in Classical Gravity, and you'll see this picture with about 15 others. But he has no proofs. His methods are similar. There's no proofs. There's parts of it he missed, but he did find it first. But we got the credit because of this, our proof and our explanation of it, which involves the shape sphere, which is the main part of this talk. So I'm going to, the same orbit is now viewed on the shape sphere. And on the shape sphere, a single point represents all three bodies. So a single point here represents a triangle. A moving triangle is this picture. So the idea of the talk is try to explain this, which was my main route into understanding the three-body problem. One more. So, like Luis said, this started a little industry, and our methods, and this is one. These people, Fusco, Granchi, and Negrini, were able to kind of use some of our methods, and for every platonic solid, get a whole family of orbits. So I just show you one of their, my daughter told me this looks like bugs to her. But anyways, this is a solution. And for each platonic solid, you have a whole family of solutions. On his webpage, you'll find 100 or more orbits like this. Okay, so that was 2011. And I think that's the end of the tour. Okay. So now we get to the body of the talk. You're going to see this picture maybe 4 or 5 times. So I'm going to try to, I'm going to explain it in several different ways. So, here's triple collision. There's triple collision. These are the solutions that Euler found. This equator represents collinear triangles. When I move out in a ray, that's just expanding or shrinking the triangle. So that's what it means to move radially outward, is to just change the size without the shape. So the sphere I call the shape sphere. You know from geometry, high school geometry, that the sphere is two-dimensional. Well, what is the shape sphere? It's a space of oriented similarity classes of triangles. So if you had a good class in geometry in high school, you learned about similarity classes of triangles, and that if you know the angles, you know the shape. There's only 2 numbers there, 2 angles, right, because the sum is 180 degrees. So this is the sphere of similarity classes of triangles. This I call shape space. This is the space of congruence classes of triangles. I put oriented here. So the reason oriented is here is because if I take a triangle and I flip it, I cannot do that on the plane without a I have to move into space to do that. So when I call 2 triangles congruent, I do not allow reflections, only rotations and translations. This is one of the Lagrange orbits, one of the equilateral triangles. This is the other, so that it's just flipped. It's flipped, or if you want, labeled differently. And then these rays coming out are binary collisions. So we're going to try to explain that, where that came from, how it helps understand the three-body problem. That's the idea of the talk. So where did this come from? So Galileo, before Newton, said the laws of physics are invariant under the group of isometries of space. And that was the principle that Newton based his equations on. So this is a group of translations, rotations, and reflections. Pretty soon we're going to cross out the reflections. The equations that I wrote down, so I call them D times N. So D is 2, N is 3. So 6 coupled second-order differential equations on the n-fold product of space. So here it's the threefold product. I'm just going to work in the plane. Threefold product of the plane. So you have this group acting on this space. As mathematicians, we form quotients. That's what we're going to do. So here's a few technical slides. General principle, if you have a manifold in a group and a differential equation that's invariant under the group, you can make it go down to the quotient space. So it's invariant under the symmetry, you quotient out those symmetries. So our case, the space is 3 copies of the plane. The group, I write iso plus of R2. It's just fancy terminology for translations, rotations. I cross out reflections now. The little plus means orientation preserving. So no reflections allowed. Q mod G is the oriented congruence classes of triangles. It's a kind of a miracle. It turns out to be regular 3 space, and I call it shape space. And it contains the shape sphere, which is the oriented similarity classes of triangles. And I've set the size to 1. Later the size will be called I. So we expect to get a second-order differential equation on this shape space here, that picture I was drawing. And it's going to be it turns out that it's going to be parameterized by angular momentum. J is my symbol for angular momentum. So this was a dense slide. I should have so another more dense slide and then more pictures. So the structure on this this is I call the configuration space of the 3 bodies. Another way to think of it is located triangles. They're triangles with the vertices actually marked. So I write points in it as triples, Q1, Q2, Q3. The Q's are in R2, and algebraically it's simpler to think of R2 as the complex numbers. So instead of using x, y coordinates, I put x comma y together to be x plus iy. And that's just to make the algebra much simpler. And this thing has an inner product. We call it the mass inner product. It's built so 1/2 the squared length of q dot. Dot means time derivative. This is the kinetic energy. So I built the inner product so the kinetic energy is 1/2 the velocity squared. There's the formula. It involves the masses. When you do that, Newton's equation has a very simple form. Q double dot is the gradient of u at q. You have to be careful what the gradient means. Gradients are actually associated with metrics. When you first learn them in vector calculus, you don't usually see that because you're using the standard metric. But here's the little formula. This is a 1 form. That's a vector field. This is the relation. This tells you how to compute the gradient. The masses are buried right there in the metric. And U is the negative of the potential energy from physics. It's the reciprocal sum of the distances with mass coefficients. When you do all that, the energy is kinetic plus potential, which K minus U. The size, I talked about setting the size to 1 earlier to get the sphere. The size is just the squared length of Q relative to the mass inner product. Physically, it's called the moment of inertia tensor. So if you imagine your triangle with masses and you freeze the lengths and try to spin it, it's how it resists spinning, the moment of inertia. all of these functions, the inner product, everything descends to shape space. We're going to push all this stuff down. There's one more thing that you can't quite push down that parameterizes everything. That's the angular momentum. Here's a formula. Here's several formulas for it. It's essentially a sum of assigned area. This is like the area. This is the area of the parallelogram spanned by Q and V. V is the velocity for Q. So that's the standard angular momentum of physics, written a little different way. So these are just the basic functions of the three-body problem. Oh, so many dense slides. Okay. So this is the densest. And in the next slide, I'm going to implement all the algebra here in pictures. So this is the located triangles, the configuration space of the three-body problem. Here's the shape space. I'm going to show you an algebraic map. It's quadratic from one to the other. So we're going to do it in two steps. We're going to divide by translation, then we're going to divide by rotation. The division by translation comes itself in two steps. One is, they're both due to Jacobi, really. I call it Jacobian normalization. And this step I call Hopf. So first we do divide by translation. That's right here. So all we do is we take the three vectors that tell you where the masses are. We take the difference. So that's this vector. It tells you, it points from 1 to 2. So that's this vector. And then we take the center of mass of that. There it is. And we connect it to the third one. So this is a trick Jacobi pointed out. What it does is if you look at what that inner product looks like in this metric, you've diagonalized it. There's one extra term I'm not going to talk about. It's the center of mass. If I put the center of mass in here also, that quadratic form's diagonalized. So I'm going to normalize now. These mu's are related to the mass. And when I do that, so when I do that, the I that I wrote down looks just like the sum of the squares of these things. So this little step here, I've mapped from C3 to C2. It's a linear map, and these are the z's. So you can think of them as just this vector and this vector. Now, I have to divide by rotations. And I want you to imagine what happens if I rotate that triangle down there. Those vectors y will rotate exactly the same way. What that means, since the z's are just rescaled versions of the y's, it means these things just get rotated. In complex variables, that means I multiply by e to the I theta, where that tells me how much I rotate by. So that's what I'm doing here. I'm trying to quotient out by multiplying by e to the I theta. The standard way to do that is to look at the invariance. So if I put a norm z squared in either one of these, that doesn't change when I multiply by e to the I theta. And neither does this. z0 times z1 bar. The e to the I thetas cancel. I put these together into one real vector. This thing, the real part and the imaginary part. That's this last thing. When I put them all together, I get a map from C3 to R3, and a little aside down here, the famous Hopf map, which Hopf wrote down probably around 1920, goes from C2 minus 0 to S2, what I call the shape sphere, and the formula is exactly the same except for a normalization. You divide by the square length of the vector, which is the moment of inertia. So that's the Hopf map. Programs here with some luck. Okay. So I thought let's see, come on. All right, there we go. So I teach a geometry class for high school. Well, they're future teachers. It's half people are going to be teachers and like a 10th future research mathematicians. And in high school, they use programs like this. This one is called GeoGebra. So maybe this is partly for myself, but I just did so I took all those formulas and I implemented them in GeoGebra. So I'll just talk through what happens. There's the triple collision, and I'm going to go one at a time through here. Let's see, yeah, this will work. Okay, that's a binary collision ray. Another binary collision ray. There's the third binary collision ray. That's the collinear plane. So that's all right there, those are collinear triangles. There's the shape sphere. So now I've set that I equal to 1, that z0 squared plus z1 squared. That's the shape sphere intersected with the equator. So that's collinear triangles viewed on the shape sphere. That's Lagrange point number 1. That's that first solution of Lagrange I showed you, if you want. Oh, come on, keep going. There's an Euler. There's an Euler solution. There's another Euler solution. There's the last one on the other side, and there is the last Lagrange point. So that's the shape space, and that's the shape sphere. And the formulas, I just implemented it with the formulas. Okay. So now we will see a little bit what the map looks like. Okay. So once I'm going to move this triangle around, and I want you to look at the point on the, you see there's a sphere and a triangle. So this is the actual map itself in GeoGebra, okay? So let's move ourselves once around the equator if we can. Let's go, okay, there, you see binary collision? I keep moving. And now I want to keep going around the equator. I make another collision. I keep going. Can someone tell me how to hit that red point on the equator? And I just keep going, huh? Okay, so there I just explored the collinear triangles. Let's go up to Lagrange. So here's the equilateral triangle, should be somewhere in there. Come on. Well, that's supposed to be equilateral, huh? Pretty close. And now I'm going to just move this, I'm going to try to keep it isosceles the whole time. Move this down, and right there I go through the Euler point. The masses are treated as being all equal here, and then I just go down like this. I've just made a curve of isosceles triangles on the shape sphere. It makes half of a great circle. If I kept going and going and going, bigger and bigger and bigger, it would be the same as making these closer together, and eventually I would limit to a binary collision like that. Okay, so that's the map, that's the shape sphere, that's the main part of the talk is that map and then using it to understand the three-body problem. So maybe just for our imagination, you can imagine these 3-point masses moving around in any one of those figures I showed you in the tour. They could move around in the figure 8, for example, and then you would have a corresponding motion here, huh? And the point is, the whole point of the map is the configuration space of the three-body problem is 6-dimensional, 3 points in the plane. Our minds are not so good at visualizing in 6 dimensions, but we're quite good at visualizing in 2 dimensions. So if if I can really understand this map, if I can translate something 6-dimensional and something 2-dimensional, then I can have a chance of solving it. So that's the real point of the talk. All right. This is a picture Rick Mokel made for one of our papers. There's an energy that I hid. So this is, again, that shape space. There's something that's very important in mechanics called the Hill region, and when you fix the energy, there's a reason to always have the energy be negative. When you fix it to be a negative constant, the Hill region is the part of shape space for which there is a possible velocity. So this is the domain where the motion occurs, and the way you actually compute it, I had that negative potential called U. It's where U is bigger than H. Because of the 1 over R's in the U, the binary collision rays are right here. The U goes to plus infinity there. So as I increase U, you'd pinch down on these rays. So this is where the motion happens, inside there, when you're working in shape space. Okay. This point, that's supposed to be the shape sphere. I don't know if you can see it. So there's 5 directions I can go in. I'm just going to tell you briefly about the 5 directions. There's papers for each of these. The directions I'm going to follow are, I have another one of these. Oh, there it is. Okay, I got to hold it hard. I think it's ooh, it died. All right, well, I can use my hands. We're going to follow the figure 8 direction, but I just want to tell you a little bit about the other ones. I guess I'm focusing on the methods. This uses variational methods to get the figure 8 and discrete symmetries. Not long after I did the figure 8 paper, I did a paper that used something called the Jacobi-Maupertuis metric. It used more Riemannian geometry in the curvature paper, hyperbolic ants. I was able to prove the uniqueness of the figure 8, but I had to cheat. I had to turn the force from Newton to a different force called the strong force. So there's this paper. Here, Mark Levy made a crucial contribution here, and some mechanical intuition, which I think maybe I'll say a little, no, maybe I'll just do this. Anyways, the result of that was a theorem that said if the angular momentum is 0 and the energy is negative, then every solution goes collinear. Collinear means, in astronomical terms, it's called a syzygy. So the paper is called Infinitely Many Syzygies. And there's a single exception to that. It's this Lagrange collision ejection orbit. Remember where they exploded? The only exception. A year ago with Rick Mokel, or maybe a year and a half now, we proved a theorem I've been working on for 17 years. I thought I'd never prove it. It used a different technique called blow-up. So that's the top here. And what I decided to talk about is a thesis work of a guy from Australia named Danya Rose. Maybe tell you a little bit about his methods. And he has the appendix to his thesis is over 700 pages with about 350 new orbits. So, well, I don't know how many of them are new and not, but so I thought I'd tell you a little bit about this and this, and maybe if there's questions, we can go back to this slide. And I mean, there's just too much for me to talk about to try to cover all those things. So we will go to the figure 8, Danya Rose thesis. Okay. So the thing that motivated my work was something I knew from my classes in Riemannian geometry, which is if you have a compact manifold and you fix a free homotopy class, so that's a loop on the manifold up to deforming it, then in every free homotopy class there's a periodic geodesic. So that was the motivating example. Method of proof is the direct method of the calculus of variations. You minimize the length over the given homotopy class. So I wanted to do that. I was inspired by a Berkeley professor named Wuyi Shang. I wanted to do that for the three-body problem. The analog of the free homotopy class is what I call the syzygy sequence. So maybe we'll go to the next slide so it looks bigger. So as I move along in the three-body solution, I become collinear at various instants. Every time I become collinear, I mark what body's between the other two. So in shape space, what that looks like is I've taken that equator. What I've done, I've taken the equator, I've turned it into the line, I've sent one of the collision points out to infinity, and I've just marked. This means 1 is between 2 and 3. This means 2 is between 1 and 3. This means 3 is between 1 and 2. Up here, they're not collinear. So as I move around, I cross this axis. And as I cross, I get a sequence of numbers. The numbers for the figure 8 is 1, 2, 3, 1, 2, 3. So basically what I wanted to prove is for any sequence you write down, there's a solution that has that sequence. That is still open. That was the motivation. I wouldn't have been able to work on the problem without kind of that. It was a big goal. I didn't get it, but we found this, rediscovered this figure 8 instead. So here's the actual method. This is a Euler solution. This is an isosceles great circle. They're disjoint. I'm going to minimize something to go from here to here. The something is 2 slides back. It's called the action. Can you see down here? So this is the classical action of physics. It's kinetic minus potential. My plus u is minus the physics v, because u is positive for the n-body problem. The potential is negative. So that's what I'm going to minimize, and thank you. I minimize that over the shape space, but it's easier to draw the pictures in the shape sphere. So I'm going from here, ooh, nice and bright. I'm going from here to here, huh? So the theorem is the minimum exists. Now there's a thing we all know from daily life. If I'm trying to get from here to the back of the room as fast as I can, I hit it orthogonally. That means I hit here, I hit this ray orthogonally, I hit this isosceles plane orthogonally. This is going to be 1/12 of the overall solution. So let's see if we can find questions. See if we can get this one might bomb. We're going to open recent. And every other time I do it, there's too many steps in here. This one bombs. We'll see. Like the communication here. This. I'm going to quit. I'm going to quit this and see if I can. Oh, it worked. Okay. Great. The other one, let's step through it. So I'm going to build up my planes. That's one of the isosceles planes of symmetry. I didn't tell you what that meant. These isosceles planes are symmetries. When the masses are equal, I can switch the place of 2 of the masses. In the shape space, that corresponds to reflecting about the isosceles plane. So I have symmetry. Those are my discrete symmetries. So I have a bunch of discrete symmetries. The figure 8 only exists when the masses are equal. So there's another plane. There's the sphere. Okay, there's the 3 planes of symmetry. You can see them. And over here, we can spin it around. Come on. There. Okay, there we go. Okay, that's what I call our test path. That this is not, I didn't use numerical data. This is just I splined something in to make the picture. So this isn't the actual figure 8 on shape space, but it's a curve that hits the Euler line orthogonally, and it hits the isosceles plane orthogonally. And what I'm just going to do is implement the reflections. Do what? They just flip the 2 masses. They're symmetries of the solution, and they let me dance across. There. So you can see the other one there, and then we have another one in a little bit. On there now. Nope, not yet, but it should appear. So we've got 3 arcs like that, and if you keep doing this, I think I put one more in. Put one more in if there is. Put 2 more in. You get the picture, though, I think. It just starts slowing down once I put all these things in. All right. I hope that gave you a little bit of this sense. I just made 1/2 the figure 8. There's 6 congruent segments there. If I go all the way around, I've come exactly back to where I started. And that's what the figure 8 looks like on shape space, and then you have to do some work to figure out what it actually looks like. So that is that solution. 10 more minutes, is that right? Or am I, yeah? 10 to 15? Okay. So let's go back to the let's go back to the talk. We did that. Okay, so I want to tell you a little bit about this person's thesis that I was a reviewer of. They paid me, but I've never been paid to review a thesis before. But this thing was over 800 pages. Now, I didn't read the whole thing, but the work was really, really good, I thought. So he calls it the bestiary of periodic orbits, 2016 thesis. He worked with Holger Dahlen. So let's look at a little bit of the bestiary and maybe talk a little bit about his methods. Okay, so couldn't have done it without work of Levi-Civita. So when you go to bind BO, for him, he has a different labeling system, and I like his labeling. He's for binary. A is acute isosceles. O is obtuse, wide isosceles. M is midpoint. That's the Euler. C is collision. So that's his system. In any case, when you go to binary collision, the equations blow up. They become infinite. It's hard to make sense of them, and they make a mess of numerics. If you get really close, your forces go to infinity. It's a mess. Levi-Civita, the Levi-Civita connection guy, in around 1912, told us how to regularize a single binary collision. It's called Levi-Civita regularization, and it involved something like a branched cover. Atra, who's the guy who's credited with the Big Bang, it's great to read about him on Wiki. Priest. Lemaitre regularized all 3 binary collisions at once. And what we, and he, in a sense, so I guess I'll just tell you what I know, which is my own paper, but it certainly builds on all these people's paper. In a sense, Lemaitre has basically done what we did. We said it in a different language. So let me try to say what the end product is. The end product is here on the shape space or the shape sphere, the equations blow up at 3 points, a binary collision, or 3 rays. You regularize all of them in a consistent way, and the equations are defined everywhere. There's no singularities. That makes it great for doing numerical integration. Now the map itself, but you want to understand what you did. So you need to understand the map from here to here. The map is a 4-to-1 branched cover. So each point here has 4 inverse images, with the exception of the binary collisions, which are the branch points. So the branch points each have 2 inverse images. Those are the binary collisions. They're what's left over up here. Equations are regular, so this B went to that B. So the best way, I didn't have a great picture here, the best way I have to visualize it. Remember those planes that I was drawing and how they cut space up? And they cut the upper hemisphere up into 6, right? Here's a good way to say it. So don't cut it up into 6. Cut the upper hemisphere up into 3. So just take the 3 binary collisions and connect them to the North Pole. You have a spherical triangle. That spherical triangle, its inverse image under this map is the entire upper hemisphere. No. Is that right? Yeah. Okay, so when all the dust settles, what used to be the 12-fold symmetry that we used for the 8, if I had reflected all the pieces, there would have been 12 of them, becomes a 48-fold symmetry because there's kind of extra sign flip symmetries. So he integrated the equations over here. That's what Danya Rose did. And he kept track of the group theory associated to the orbits. And what he got were 350 pages like this and 350 pages like that. And I'll just tell you a little bit about what the numbers mean. He tells you the isotropy group of the orbit, so he has generators. Tells you what the isotropy is. Sequence type, this is obtuse, collision, acute. This thing hurts my eyes. Okay, so A is acute, O is obtuse, C is collision. So he tells you how it's cutting. It's the cutting sequence as it goes into through the regularized shape sphere. Here are eigenvalues that have to do with stability and dynamics. This is various periods. This is the geometric phase. So, and let's just look at one of his many orbits. I can put it on play. Okay. So you get to see it on all 3. So this is in inertial space. This is periodic orbit. You can see the 3 bodies. This is what it looks like in must be the this is the unregularized shape space. This is the regularized shape space. Okay, that's all I had planned. I'm hoping, I think I have a little bit of time left, but